Alright, here are some other ways that you can use the ideal gas equation. This one is pretty much PV equals nRT, just rearranged, so that instead of volume, you have molar mass and density in the equation. If you sit there and think about it for a second, you can see how the units for molar mass, density, and volume could all work out. So when you're talking about gases, the density is in grams per liter. Please remember that. Gases aren't very dense, so it takes a whole lot of volume to equal a gram. That's why it's in grams per an entire liter. Whereas when you're talking about solids and liquids, they are much more dense, so we measure them in grams per milliliter. So if you know... I knew you were going to do something. Oh, sorry, that time it's not my child's fault. It's my 41-year-old child being a turd. All right, if the density, temperature, and pressure of a gas are known, then the molar mass can be calculated. And then from that, if they give you a hint, you can figure out what the identity of the gas is. For example, if they say it's a diatomic molecule, you know it's something like oxygen, O2 or N2, or they tell you it's a non-metal oxide or something, you can figure out the identity of the compound, the gas. All right, so remember, density is mass over volume. So here's a sample problem. 98 milliliters, I don't know why my nose itches every time I try to make a video. All right, 98 milliliters of an unknown gas weighs 0.081 grams at STP. Standard temperature and pressure, which is room pressure, but really cold. Calculate the molar mass. Well, remember density is mass over volume. And when we're dealing with gases, we have to have our volume in liters. So STP, standard pressure, is 1 atm. The volume, I went ahead and put it in liters already. Standard temperature is 273, and our mass is fine to use just what was given here. So density is grams divided by liters, so I just plug that in here. R's always 0.08206 for us, and plug in the temperature and the pressure, and the molar mass is 19.10 grams per milliliter. So it's probably neon then, since it didn't tell us it was like a diatomic gas or anything. And if we look at the periodic table, neon's molar mass is fairly close with 20.81. And you guys have done enough labs at this point to know that you seldom get exactly the right answer in a real experiment. All right, here's another way of using the DRT over P formula. What is the density of carbon tetrachloride vapor at 714 torr and 125 degrees Celsius? This one, you know the identity of the gas, so you could figure out the molar mass. And this time we're looking for the density, so you just solve for D. A lot of people get stumped on these and sit there thinking, God, I only know the pressure and the temperature. What am I supposed to do? Well, no, you know more than that. You know the molar mass because you know it's carbon tetrachloride, carbon with 4 Cls. So this is worked out in the other video by hand. It's one of our sample problems. Okay. Okay. This is another sample problem, I believe. Or no, it says not in notes, so possibly not. All right, a half mole sample of oxygen is confined at 0 degrees in a cylinder with a movable piston, so just like the syringe plunger thing. The gas has an initial pressure of 1 atm. The gas is then compressed, so it's squeezed by the piston until the final volume is half its initial volume. The final pressure of the gas is then 2.2 atm. What's the final temperature of the gas in degrees Celsius? It says to try this one yourself because there is more than one way to do it. We know, according to one of the gas laws, the Gay-Lussac law, that pressure and temperature are inversely proportional. So here, I'm skipping ahead. We know, according to Boyle's law, that pressure and volume are inversely proportional. So when we compress the gas to half its initial volume, then we should double the pressure, right? So when you cut the volume in half, the pressure should go from 1 atm to 2 atm. But the pressure went up a little more than that. So that means something else must have changed, like the temperature. So it was 0 degrees originally. As they compressed the gas, they must have raised the temp a little bit also. So how could we do this? There's a couple of ways, and some are faster than others. Okay. The right answer is 27 degrees Celsius. So I want you to try to do this. And how would you figure this out? Would you do two separate calculations using two different laws? Would you use one law? There's not really a right or wrong way. The better way, of course, is the faster way. All right, so all these formulas are the ones we've covered so far and these will all be provided during the test, given, how to convert from Celsius to Kelvin, although you probably have that memorized. Then whatever pressure units I'm expecting you to convert between, I just put a few of them on here. You'll be given that. You'll be given R. Even the volume of a gas at STP I'll give you. Boyle's, Charles, Avogadro's, the ideal gas law, combined law, molar mass, dirt P, and density will all be provided during the test. So if you're worried about that, this isn't about memorization. It's more about conceptually understanding gases. Okay, there is a gas law song. I'm not going to sing it to you. I've lost my CD. Okay, I won't say lost. I've temporarily misplaced my CD. But it is funny if you want to pause and read the lyrics. Just that my favorite part is that T measured on the Kelvin scale. Remember that, or you might fail, because you definitely don't want to forget that. Okay, and probably my favorite thing to do with the gas laws is stoichiometry problems, because I just like stoichiometry problems. So, volumes of gases in chemical reactions. So, if you look at the end of this here, it says moles of nitrogen to moles of NaN3 to grams of NaN3. Moles to moles, moles to grams. Nothing new here. The only thing we're going to add is just happen to use gas data and use some kind of gas equation to get to moles. Or possibly we'll use a gas equation at the end to find out about the gas. But it's just one new little thing we're going to add in where you are given pressure, volume, and temperature or so, and have to use that to get moles. And then you just do stoich like usual. All right, so gas stoichiometry. This is a shortcut that you guys are already very knowledgeable about. The volume of 1 mole of gas at STP is 22.4 liters. 22.41 if you're wanting to be more exact. So this is just yet another conversion factor to add to our arsenal of conversion factors. So here's a simple example. Sample of nitrogen gas has a volume of 1.75 liters at STP. How many moles of nitrogen are present? Okay, well, we know the volume is 1.75 liters. We know the temperature is 273 Kelvin because it's standard temperature, and we know the pressure is 1 atm because it's standard pressure. So we have P, V, and T. Easy enough to use PV equals nRT to solve for moles, right? But because it's at STP, we can skip the algebra and just use the 22.4 number as a conversion factor. And it would look like this: 1.75 liters times the fact that there's 22.4 liters on bottom to every 1 mole of gas at STP. And there would be our answer. Now, it's the same answer we would get. Oh, I thought I had it there. Sorry. That's the same answer we would get using PV equals nRT. This is just easier and much faster. But please don't get 22.4 happy and start trying to use this constantly. It is only for gases, and I've seen some of us try to use it with solutions and stuff, but it's only for gases, and not only that, it's only for gases that are at STP. All right, so another example: how many liters of carbon dioxide gas will be produced when 152 grams of calcium carbonate decompose at STP? Okay, so it's, once again, helpful to keep an eye on which chemicals are gases here. Okay, we're wanting to know the liters of carbon dioxide, the liters of gas, And we have 152 grams here, but that's not of carbon dioxide. That's of calcium carbonate. That's this stuff. So we're wanting to know how many liters of gas will be formed from 152 grams of this substance. So make sure to pay attention to the chemical involved. So we have 152 grams of calcium carbonate. Grams are useless, so we convert that to moles. Then it's a 1-to-1 mole ratio. And then because we're at STP, we can go from moles of our gas to liters of our gas using the 22.4 shortcut. Could you stop and get moles here and then plug it into PV equals nRT? Sure, you'd be wasting your time, but you'd still get the right answer. All right, which would be 34.1 liters. All right, how many molecules are in 22.41 liters of an ideal gas at STP? Hopefully this is fairly easy for you to figure out. How many molecules are in a mole is really all that we're asking, okay? And this is what Avogadro essentially figured out. Amedeo Avogadro did not figure out the 6.022 times 10 to the 23rd molecules part. That came much later when people had like better equipment and for measuring. He just realized that if you had two different containers of two different gases that were of equal volume and were at equal pressures and equal temperatures, well, then there was the same number of molecules in each container, even though it was two different gases. All right, so gas stoichiometry. Again, we've looked at stoich using masses and molar masses. We've looked at stoich using molarities, concentrations, and volumes. And then now, yay, we can use it for gases as well. Okay, so we've gone grams to moles, moles to moles, moles to grams. All we're going to be doing is the same thing, just throwing in some gas data. So we can get to moles instead of by using molar mass or molarity, we can get to moles of a gas using PV equals nRT. Either we can start with our gas or end up with a gas. Either way. And then at times, instead of using PV equals nRT, you'll get to use 22.4, but that's only if it's at STP that you can use that shortcut. All right, ammonia and H3 gas can be synthesized from nitrogen gas and hydrogen gas. What volume of ammonia at 4.44 atm and 80 degrees Celsius can be obtained from the complete reaction of 7.5 kilograms of hydrogen? A lot going on here. As always, your first step is to set up a balanced equation. We got to have that. Okay, so we got a mole of nitrogen reacting with 3 moles of hydrogen, and that will produce 2 moles of ammonia. Everything's a gas in this equation. We're wanting the volume of ammonia, so the volume of product, and we're reacting 7.5 kilograms of hydrogen. Okay, voila. That's really all we have here. Now, thing to remember with this one is that we're not at STP. We're at 80 degrees Celsius, which is 353 Kelvin, and we're not at 1 atm. We're at 4.44 atm. So there's no way to get around using PV equals nRT this time. But first, we need to get moles of ammonia, and the amount we're given, the mass we're given, is not the mass of ammonia, it's the mass of hydrogen. Okay, so we'll have to do good old-fashioned stoichiometry to get from mass of hydrogen to moles of ammonia. Then we can do PV equals nRT to solve for volume. Whee, fun animations. All right, so we need moles of ammonia, not hydrogen. Okay, we need a stoich mole ratio here. A lot of times I see people will just take this mass, convert it to moles, and then plug it in here. Okay, well, if you take your mass of hydrogen, convert that to moles, and plug it into PervNert, well, you can get your volume of hydrogen, but that's not what the question wants. It wants the volume of ammonia. So as always, it's extremely important to pay attention to what chemicals you're given and what chemicals you're looking for. All right, so we have 7,500 grams of hydrogen. Going to convert that to moles using the molar mass. And then we're going to convert that from moles of hydrogen to moles of ammonia using the coefficients. And there's a whole bunch of moles of ammonia. That's a lot. And it makes sense because we have 7.5 kilograms. You know how light gases are? Hydrogen's especially light. A hydrogen balloon would float even better than a helium balloon, except it goes flat a lot faster because the molecules are even smaller than helium's, but I digress. It makes sense to get a big number of moles here because we reacted so much hydrogen.